It's a great pleasure to give this talk. It's a joint work with Mark Rowland from University of Cambridge, now DeepMind, Wenyu Chen, MIT, and Adrian Weller, University of Cambridge, and the Alan Turing Institute. So what's the subject of this talk? We would like to give a unifying view of different recently proposed approximate Monte Carlo methods that improve standard baselines. So that's the approach, that's the task that we are interested in. We would like to approximate expectations of this form, where the distribution is an isotropic distribution, for instance, Gaussian. The standard Monte Carlo approach here, where xi's are taken independently at random from that distribution. And of course, the Monte Carlo methods, lots of applications in machine learning, dimensionality reduction, random feature maps to scale kernel methods, also in evolutionary strategy methods, and many, many more. So recently, new methods for doing Monte Carlo were proposed for those types of expressions where we condition on different samples to be exactly orthogonal. It turns out that, but the marginal distributions are still the same. It turns out that they lead to more accurate estimators for lots of applications. But the problem is that creating such an ensemble of orthogonal samples is expensive. It's cubic in the dimensionality of the data. So even more recently, lots of methods, approximate orthogonal Monte Carlo methods were proposed that are much more computationally efficient, but interestingly, at the same time, often provide accuracy improvements. And there is literally a zoo of these methods recently proposed, some based on the products of random Hadamard matrices, when the randomness comes from the diagonal matrices, and the orthogonal structure is induced by the Hadamard matrices. The samples there are really given by the renormalized rows of those matrices. Other setting would be Katz random walk matrices. It's pretty much constructed by doing a random walk on the orthogonal group, and some other constructions, butterfly matrices defined recursively right here. Those different constructions look really like very different at first glance, but they share common properties. They provide computational speedups and very often accuracy gains at the same time over standard Monte Carlo baselines. So they give us free lunch theorems like in that setting. Now the question is why? And we are coming up with the unifying view for those constructions. Basically, what we say here is we can think about all of them as manifestation of the same basic rule. These are products of structured Gibbons rotations or Gibbons reflections. We'll call them Gibbons transformations. And they are composed in different ways for those different classes, but these are the building blocks. These are those elementary particles that are building those matrices that define the samples. Example, Katz random walk matrices, just the product of independence Gibbons rotations. Products of Hadamard random chains can be also viewed as products of Gibbons reflections. An example here, those matrices F tilde JL I presented here in the rows on that picture. And the same is true for butterfly matrices. Now, this unifying point of view gives us extra advantage. We can actually prove theoretical results regarding those constructions. To the best of our knowledge, we are the first to propose theoretical results showing that we can get not only computational but also accuracy gains using those approximate orthogonal Monte Carlo methods in the nonlinear regime. That's this theorem right here. The accuracy gains are basically implied by those mean squared error inequality, and the computational gains come from the fact that the number of Gibbons rotation that we use is just slightly superlinear in the dimensionality of the problem. Now, all this stuff is really implied by deep theoretical mathematical results recently obtained by researchers from Harvard University, basically analyzing the total variation distance between the Haar measure on the unit sphere and the distribution induced by the action of the Katz random walk matrices on the given unit vector. And this more careful analysis that we provide here leads to the theoretical results that we give. And these are some of the experimental results. On the left-hand side, the kernel setting, first two plots, accuracy gains if we use this approximate orthogonal Monte Carlo constructions versus baselines, which is IID in the blue line right here. And the next two plots is computational gains, so free lunch theorem. Maximum mean discrepancy experiments showing the comparison of the total variation distance between the Haar measure and the one induced by the matrices that we analyze here, as well as reinforcement learning experiments where we actually show that we can use these constructions also to come up with more efficient ways of doing Monte Carlo estimation of the gradients of Gaussian smoothing in the ES setting. More details in the poster, number 199, and it was a great pleasure to give this talk. Thank you so much.